Okay, so the next presentation at the joint GEM CEDAR session will be a presentation from Jasper Gerloff giving us an overview of some of the questions that we can ask in the important arena for both GEM and CEDAR about magnetosphere-ionosphere coupling. Jasper is a scientist at the Applied Physics Lab and an expert both on the data and the modeling side, so I look forward to hearing what Jasper can tell us about the system.
Okay, I guess, well, half of the people out there, we still get started and maybe they will drift in. Is that okay? Just say yes. Thank you. Okay, so the title here is How Can We Investigate, let me see my glasses here, Global Magnetosphere-Ionosphere Coupling. And I think there's a key word here, which is global, and I'll get back to that. That's a very challenging task. But before doing that, I want to say thanks to my co-authors, Shinotani, which I work with basically all the time. Robin Barnes, who is effectively the guy that makes everything possible. So we think of it and he makes it possible. Fantastic guy. Colin Waters, Mutoba, and the last one is Cameron Olsen. He's an undergrad who has done several things that I'll show you today. He's a wonderful guy. So the key word here is global. How on earth do we address that? That is a very big task observationally. But we have new tests, our data sets that allow us to do some of these things today. If you look at this movie, there are 3 different data sets plus an extra. And the extra one is important. If you look to the left, it's Ampere data. So Ampere is really the Iridium constellation of satellites. On board them, they have a magnetometer. Really only an attitude mag, so it's a terrible magnetometer, but Brian Anderson had this wonderful idea that even if you take low quality data, but you take a lot of it, you might be able to do science. And it turns out he was able to pull it off, and it's wonderful. So now we can get global distributions of Feline Currents. This is the main coupling mechanism between Earth and space, and near space. I don't know why it's not running. Is it running now? Okay. You saw it, right? It was a good movie. Okay, well, close enough. The center one is Superdome, which is a global network of HF radars. And if you look at their measurements, and you can, in some sense, take these line-of-sight measurements and compile a global map of the ionospheric convection. On the right, you have Supermag, which is magnetometers distributed around the world. And the final one on top was SUSI measurements, which is an imager that is flying on several DMSP satellites. Oh, and here we go. Perfect. Okay, so you see that these data sets in principle, we can combine them in first principle and we get full solutions, including conductances, flows, currents, you name it, energy deposition. But of course, it's not straightforward. And the talk today is really, how do we take these data sets and utilize them to get the insight into the system behavior that we seek. Okay, so since I have quite almost an hour here, I thought I had an outline. Maybe it's needed. So the outline is that how do we basically derive these global distributions from these data sets? And at the bottom, you see 3 pictures from the Polar low-res camera. It was flown, it's part of the Earth camera package that had 3 cameras. This particular camera is very high resolution, even though it's called the low res. And it shows, of course, the aurora and how it's active. Even though it's low res, it's a very high resolution camera, but they had no geolocation. So what do we do with these images? Well, if you see at them, there's about 4 to 5 minutes in between. And you see structure and variability. You see it's not a static picture. And this is really the problem we are trying to understand. This is the system we are trying to understand and investigate. And as you see, this is a challenge. It's not static, and it's highly structured. So how do we do it? Let's start with the top. So here's the problem. Here's from Supermag, a movie, and you see a substorm, a typical substorm, and each dot is, of course, a magnetometer. And you see the variability and the evolution here. But, of course, we don't have perfect spatial coverage. And I can pretty much guarantee you that your particular problem is where you have a data gap. That's where the key is for you personally. And you will call me up and say, yes, but why don't we have a mag right there? Okay, that's just Murphy's Law. So what do we do about it? Okay, so we can see here, for example, here there are 3 question marks. One could maybe ask a question, well, how is the connection between the day side and the night side? How are the currents flowing from the day side to the night side? And this would be this particular question mark. Another one may be, how do you feed the Aurora electrojet system? And how do you drain it? That's something we see at mid-latitude, but of course it's over the Atlantic, where I guarantee you we have no mags. And finally, you may be interested that why do we have currents apparently flowing here post-midnight towards midnight, where it gets very intense, and then it seems to end. It seems to end, so the question is, of course, is what is going on right in that region? Does the current flow up, or does it terminate here, where you have this big emission blob here? That's a key question, but of course there's no mag there. Darn it, right? And even if we had mags, how do we interpret the data here? Because these are not straightforward to interpret even. Okay, so we have some challenges on our hand. So to fill in these data gaps effectively, I guess there's 3 different approaches here. You can just do interpolation. That makes assumptions as to the scale size of the features. Can you really just interpolate over your data gaps? Is that a reasonable way to do it? The other one is that you could use some intelligence or some prior knowledge. You say maybe the system is driven by the solar wind or controlled by the solar wind. Okay, so we bin the data and then we fill in data using these solar wind conditions. So we have some knowledge and we hope that that works. Or the third one is you'd use what I call the state descriptors. It could be indices or something, and you say these describe the state of the system. And then you fill in data using that system before interpolating. So you have different ones, and I'm going to discuss the advantages and disadvantages of all of them. Okay, so here's an example. Ampere data is really, they don't do, strictly speaking, interpolation between these orbit planes there's 6 orbit planes. But it's kind of what they do. So let's just assume that it's interpolation. You can do that for this, but of course then I may ask you, what is going on between these orbit planes? Is it reasonable to just interpolate across this? Are we going to lose an understanding of what the physics is going on there? Of course, we are only going to be able to see large-scale sheets since this is the separation, and we really got to ask questions as to whether that is applicable to our problem. And throughout the talk, I'm going to emphasize, don't just take data, specifically interpolated data, and apply it to your problem. Think carefully about the coverage and what has happened to this data prior to making any conclusions. It's a real pitfall. Okay, so question, are the scale sizes of the features larger than the spatial data gaps? And the answer, of course, since I'm a man of strict opinions, and you can't rock me, the answer I give you is no, yes, maybe. Okay? So that I stand by that answer. Okay? The reason why my answer is that is, of course, it depends upon your question. You might be interested in global phenomena. Maybe you're interested in global large-scale phenomena in each hemisphere, so Ampere is sufficient. Well, maybe you're interested in some of the smaller scale features that you saw in the emission pattern and say, this is the physics I'm interested in, and you're not going to capture that. So bottom line is, be careful, and the answer to that question really depends upon your problem. Well, there's another one that Superdome uses. Effectively, what they do is, they take the data, they're sparse here at the top, then they use fill-in data to constrain the model. They use a spherical harmonic fitting to basically come up with a final solution, and this is what you see. Now there's a red box at the bottom here, which is really, really important, because you see that is the solar wind conditions, or more importantly, it's the model they use to fill in data. And you see it's switching back and forth between models. It'll switch back and forth. And what that effectively means is that it does pick each of these solar wind statistical models. It says, right now I'm using this bottom left here. A second later, a minute later, I use this top. And I don't know why these pointers are not working really well. So we have no pointer. Okay, close enough. So it switches between these fill-in models. And if you look at the final solution, it is jaggedy. And the reason is that it switches between these different models for every minute. Poof, it just switches to another fill-in model, does a spherical harmonic fitting, and out comes that. So you get this jaggedy behavior that is probably questionable. Oh, okay, so you can see it, and you can see it related to how this does. And you'll see that behavior. And again, that depends upon, you have to again keep in mind what is going in here. And I did warn Mike Rohanimi I was going to say these things. So in my defense, I have other concerns later. So let's just list the concerns when you do this IMF interpolation here. There's a lot of good questions here, and there's a lot of assumptions that's going into that approach. The first one is, of course, delay. This is a cause and effect that is assumed here. So the solar wind has a certain one. The convection pattern is there's a causality here implied. That assumes a delay. What should that delay be? If you ask me, there are 3 different delays in these systems. One is that if the solar wind changes, when can you see anything in the ionosphere? I call that the response time, or people call that the response time. It may only be a few minutes. Then you have the second one, which is the reconfiguration time. So the solar wind goes from one state to a different state. When is the system sort of settling into these new driving conditions? It's very uncertain what on earth that should be, maybe on the order of 30 minutes. Then you have a third delay, which is you may change and start pumping energy into the system, Magnetosphere-Ionosphere system. It's going to go unstable at some point in time, and it's going to unload it, for example, as a substorm. That's a third delay. It's very unknown what on earth that should be. So these delays are not implied here. The way it's solved for Superdome is that there's 0 delay. Second one is there some kind of low-pass filtering? If you look at that little diagram on the right, you have the driver. It may change for 1 minute, go back to this. The response in this model, in this approach to the fill-in, is that it switches, poof, poof, immediately. I personally think that there should be some kind of a filtering effect for the MI system. Obviously, the ionosphere doesn't switch back and forth like that. It makes no sense to me. Then the history. Certainly, the history of the system plays a role here. For example, as a ring current, if it's low, the plasma sheet is loaded with oxygen, it certainly responds differently to driving than if it's not. So we need to include the history of the system. Third one is internal processes. If we bin everything by solar wind, effectively we say that the internal processes have no importance whatsoever. I think that's more than a stretch. And it is ignored. So the question is that really valid? Third one is predictability. I worry sometimes if we have a certain solar wind driver, can we predict what is going to happen? I don't think so. So there's a whole host of issues. So this was approach 2, that we use the solar wind or causality basically to fill in data. There's another one here. We can do these state descriptors. So that's what we do with Supermag. So basically, we have the same sparse observation. We have fill-in data, but the fill-in data is now provided by a multilinear regression model. And these regression coefficients are all solar wind or indices, magnetic indices, or solar zenith angle or something like that. That means that we take the entire database and at a certain MLT, MLab position, we make a multilinear regression to that. Now we later fill that in, we combine it with the data, we come up with a model. This is a linear, it's not discrete, so we don't have jaggedy effects, we don't have delay consequences, but of course we have another massive issue. To what extent do these descriptors that we use, these indices, actually describe the system? So, for this, can a scalar describe a 2D or a 3D system? It's absolutely absurd to me. For example, Rostocker, he wrote a famous paper that I really, really like. Of course, it's old, so everybody's forgotten about it. But he basically said that in order to avoid the obvious pitfalls of the AE index, it should only be used in statistical studies rather than individual events. And you see at the bottom here, here's from the Supermag. Here's a particular incident or event at this particular time. Is that, knowing that index, can we really say this is the 2D distribution? I think that's absurd. Okay? So it's a real problem, which brings us to the next problem. What does an index even mean? We use KP in our field. I have no idea what KP means. To me, KP is a 3-level index. It's nothing is going on, something is going on, and a lot is going on. Okay, that's about it. Now, what exactly is going on, I have no idea. Does it have appropriate temporal resolution? Let me beat up KP again. It's a 3-hour index. Substorms occur, the entire reconfiguration of the system takes maybe 10 minutes. I mean, 3 hours, are you kidding me? Okay, does it have appropriate spatial resolution? If I make measurements out here and my mom calls me and says, yes, but I want to know what the weather is, my measurement out here doesn't really apply because she lives in Europe. So in other words, we need to have the coverage that is able to capture the features and the behavior of these features appropriately. Okay, so we need enough stations. So let me move on. So these indices, if we use these indices as we do with Supermag, how good are they? And let me give 2 examples. Here is a ring current index. So we all use DST or SUMH. We came up with a different SUMH, which is basically a local time SUMH. So we split it up into 4 sectors. And we used all the stations available, and it's a 1-minute index. And basically, it's SUMH for each local time. And here's a typical storm. And as you see, the behavior of these different color-coded indices, different local times, is not the same as the storm evolves. That means that what you assume sym means symmetric age. It is not symmetric. It highly depends upon which local time you're at. We all know this stuff, but it's still something to keep in mind. We got to go into the late recovery phase before the ring current really is symmetric per se. But there are other features. We have the sudden commencement here. That is due to the magnetopause current. It certainly is not a measure of the ring current. So this index is designed to measure the ring current, but we just said it measures the magnetopause current. Problem 1. Well, this feature here is feline currents. It's a substorm going on. So we measure feline currents too. That's not the ring current either. Okay, we can do the cross-tail current. The cross-tail current at these stations, at these locations, really looks exactly like the ring current or the magnetopause current. You can't really tell the difference. It's very difficult. So the cross-tail current may very well show up. If you enhance the cross-tail current, it's going to show up at these latitudes and look like a ring current. So be careful. Okay, we have auroral electrojet indices. It may expand far south and contaminate your stations. So you got to be careful. Finally, we have ground-induced currents. I ignored that at these lower latitudes for the longest time, but I recently was enlightened that we have to include this. So there's another contamination effect. And then I thought, okay, at least we got it. But no, the SQ current system also could play a role because we have to remove it. It's not part of the ring current. So this is a baseline problem, and it's a non-trivial problem. I had to solve this for Supermag, and trust me, it's not easy. So we got another contamination, but now we got it, right? No, we don't. Because Malamati, sitting over here, she published this recently from the RBSP of Van Allen storm probes. And what it shows at the bottom panel is this orange background. It's the high-energy protons. So it looks like there's a background of high-energy protons in the ring current just lingering on. It is not reflected in SUMH. And the reason might very well be that if you have this slowly varying background, it's being removed by the baseline system. So not even that we got right. At the end of the day, you got to ask the question, what on earth do these ring current indices even mean? Maybe nothing. At least you got to be careful, right? Okay, let's try another index here that we use. Auroral electrojet indices. On the left, you see blue dots. Those are the 12 AE stations. And they are being used to derive basically an upper and lower envelope of the auroral electrojet system, meaning the eastward and the westward electrojets. Okay, this is great. But there are only 12 of them, and we may miss some of it. The red ones and the blue ones is what we use in Supermag. We use a lot to derive the Supermag equivalent version of AE. And on the right, you see at the top, you see AE, and then you see what we call Supermag E. There's a vertical line here. That is the onset of a substorm identified by UVI, flown on image. And as you see in the top, that line precedes the decline a little bit, but it doesn't with Supermag. You also see there's a difference in magnitude for this particular substorm. So in other words, if you use all the stations, you get better timing, you get a better magnitude measure, so to speak, and the final thing, you get better information about the location of where this system is located. And in the left panel, you see here, little contours. That is the onset identified by imaging. And the black contour is when the onset occurs, and the gray is when it's expanded a little bit. And that tells you why you have a delay in the indices. Because you see, it's not over a blue station. Of course, you can't measure it if you're not in the right location, going back to what I tried to point out. You gotta have sufficient or appropriate spatial coverage. Okay? To make matters worse, in this famous Tanskanen AS paper, she said 40% of the AE could very well be, at least during onset, when you have a big d by dt, could be due to ground-induced currents at these latitudes. So we got to be careful what on earth that means. Okay, but we might be able to do better. Here's the Supermag indices for a double substorm. So these are the global versions. But you may say, you know what, sunlight certainly plays a role because sunlight provides conductivity and it certainly is needed to drive currents. Well, let's split it up into sunlit stations and not sunlit stations, and you suddenly see that the darkness stations and the sunlit stations behave very differently, which brings you to the question that I had that little question mark in my movie. How is the connection between day and night? Does the day even know a substorm is occurring? You got to be a little careful, certainly. So you get additional information here by splitting it this way, and it allows you maybe to test these things. Okay, but we can do even better. We can split it up into local time. So basically you have local time indices. So up the y-axis you have MLT, and the x-axis you have time, and now you have a better understanding of where do these perturbations occur. Where is the westward electrode located? And for example, here you see this is the first onset, and then it dies out a little bit, but post-midnight it lingers on. But the pre-midnight, and then dies out, and then comes the second onset. So you get additional information that you otherwise can't get. So there are ways of doing this, but you got to be very, very careful. And okay, so let's compare the two. Very different approaches here. So on the left you have Superdome convection plots, which is basically driven by the solar wind conditions, what I call the approach 2. On the right you have Supermag, which is using these state descriptors. Both of them have advantages and disadvantages. Okay, but they certainly monitor the system to whatever extent we can argue. But if you look, there's the two big substorms at the end here. First, we got this long period of fairly, and you can see how the vectors behave. And then it dies out for a little while, and then comes two big substorms that poof, hit the system like that. And you can see them in a second. Here comes the first one. Almost there. There we go, almost. Oh, there we got it. And then it dies out, and the second one hits even harder. Oof. Okay, but if you notice the two plots, the topology or morphology and the temporal behavior is fundamentally different in how they behave, these two patterns. And even though the one on the right requires conductivity, it still should be related to me. So that means that if we are to combine these two very diverse data sets, we better be careful. This is not straightforward. And there are really big pitfalls, which is why we made this movie to kind of compare it at first hand. Of course, you got to sit down and look at it for a little while. Okay, so this section, let's end. Simple spatial interpolation, there are three different approaches. They all have advantages and disadvantages. I thought I would end with little conclusions, maybe recommendations, because there are lots of students. And we need much more emphasis on the validation of these models. And it's not only isolate each model, but it's maybe combine the models. When you combine them, as we just saw in the two movies, you start seeing things. Okay? We must remember which underlying physical processes are being ignored before we use it for science. And we can go through the other ones. And let me just emphasize the last one. I really think that these models should allow user input, because that would be highly educational. If you change the order of the spherical harmonic fit or whatever you want to do with the assumptions, you would get a new model fit, and it would really teach you the limitations of these models. And I think instead of just pushing it down the throat of people. I think this ability to let the user pick it is very useful. Okay, let's move on to the next one. So the derived parameters. Okay, so one thing is measurement. For example, AMPR measures dB, or measure magnetic field perturbations, but that's not what we want. We want the currents. So there's a step between there. Superdome measures, to some extent, line of sight, but we want global convection, vector. So it's not the same. Supermag measures ground perturbations, but we really want ionospheric current systems. So there are steps separating these things, and they are not trivial, so we got to be careful. Let me give you an example. Here's Ejima Pro Chamber. We all know that. It's in every single textbook, a fantastic result. But where did the data actually come from? There's one assumption before I show that. It assumes that all currents with scale sizes smaller than these region 1, region 2 can be ignored. They are not important. That's a really severe assumption, and I'm not sure that is valid. So let's see where it came from. This is from their old paper. This is the data from that paper. All that structure is being ignored. And in fact, this is what it would be. I don't know what that red box is, but anyway, this is what the model would be if you're flying through. As the satellite is passing through the oval, you would see that V. That should be the same as the top, the measurements. There's significant differences. What on earth is that due to? Okay, we ignore all that small scale stuff. Is that valid? Okay. There's another assumption going into this model, which is really very serious. The observed magnetic field perturbations are due to static currents, right? As you're passing through with your satellite, it takes time. It may take a couple of minutes. Over those couple of minutes, you get a trace like you see at the top left, and you assume this is static. You're going through a static structure. Is that valid, that assumption? Well, let me give you an example. So I live in Washington, D.C., or just northeast of it. And my daughter, my little girl, she goes to the University of Richmond. Okay, and I like to visit her. So I might leave in the morning, and I realize on my iPhone it's 22 Celsius. I drive 4 hours, and I get there, it's 31 Celsius. Now I have the problem. Is that difference in temperature due to me moving to a different location, or is it due to time passing by? I have no way of telling. Zero. It's the exact same way as the satellite is going through, but we make the fundamental assumption that it's static, time doesn't matter. That's a very serious assumption. And it cannot just be waved under the carpet, so let's look into it carefully. And ST5, the satellites, they allowed us to do so because they had 3 satellites in a pearl on a string configuration. And this is from Jim Slavin's paper. 3 satellites, color-coded here for the particular pass. And as you see here, the currents they derive, they're completely different. There are regions where it's the same, but there are also regions where they completely disagree. So what we know from all this immediately we see is that the currents are structured, number one. It's not 2 sheets like in the Ejima Pro Chamber picture. There's lots of structure in there. And they're dynamic over the 1 to 6 minute difference that they had in this particular one. So we did a study for the entire ST5 database, and here are 2 different passes compared with separation of what? 15 seconds, just a few seconds. And as you see, the 2 satellites agree to a large extent, but there are also differences. You see little differences here and there. Okay, that means that even over 15 seconds, something is happening to the system. We can go to a minute, and we see bigger differences. We can go to 10 minutes, and suddenly, even large-scale currents have changed sometimes. Not always, but sometimes. So it looks like this large-scale system of features seem to be more persistent than the small-scale structures. So we can do this in like a 2D plot where we have scale size. You know, how big is this stuff? And what is the satellite separation, or when do we come back and measure it, so to speak? If we wait very little time and we're looking at very large features, we would expect that it's highly correlated. This has not changed. That was what the data should look like. If, on the other hand, we look at tiny scale size and we come back 10 minutes later, we don't expect to have any information. But what on earth is going to go on in between? We have no idea how to separate these regions. So we performed the study statistically, and this is what we got. Lo and behold, it actually works. This is not trivial if you think about it, because it assumes that the system is repeatable. It has some underlying behavior. For some reason, it could be that it just does whatever it wants to do, and then the entire thing would be white, but it's not. There is this high correlation region. So that means that the large-scale features are more persistent than the small-scale features. And it actually, you can kind of separate when these things changes. We can zoom in, and, split it into Dayside and Nightside, and you also see there's a difference between Dayside and Nightside. So in other words, the Dayside doesn't behave the same as night, and we got this peculiar break here if you look in the Nightside. So it's basically linear, and then there's a break, and another linear. On the Dayside, there's one, and then it all goes to heck. It all just breaks up. We interpret that as what's happening is that on the Dayside, the system, you have some controlling parameter, delays in the system. And then after that, it's solar wind control. So whatever happens to be the solar wind conditions during this particular, all these passes, is what's going to happen. The solar wind controls the Dayside after a few minutes. On the Nightside, on the other hand, we got the plasma sheet. And this is the plasma sheet. And you could maybe get the hint that up here it breaks up. So maybe after some 8 to 10 minutes, the solar wind goes back and controls again. The plasma sheet has had time to reconfigure itself. That was the way we interpreted it, after much debate. If we zoom in, we can see how nice it actually is, but there's also dependence on night and day. And here's the cool thing. We assume the satellite as it's going through to be static. Well, we can test that. Here's the satellite, because we know how fast it moves. So on the night side, it's typically in the blue, meaning it's correlated, and we can actually assume, typically, that it is static. On the day side, it's only marginally. So you have to be very careful to assume what you're passing through on the day side is actually static. It could be dynamic, galvanic. Well, if you're on a rocket, it's much worse. You move slower, and you can never assume it to be static, in my mind. You have to have some supporting observations, raw imaging or something. Okay, my student Beate, my graduate student, she did a fantastic study that came out so beautifully, so I have to show it to you. She did the same. She tested these currents because she looked at raw emissions, all-sky cameras, and she did a 2D FFT to look at the scale sizes and how they behave, basically the same type of study. And what she found was, again, blue, and then this black line, jaggedy, is separating the highly and the low, somewhat arbitrary. But look, there's a dotted line behind. That dotted line is from the ST5. It's a completely different parameter, completely different technique, and yet they agree. So it tells us that even though emissions is a different electrodynamic parameter than the currents, they seem to have an underlying behavior that simulate each other. I think it's a beautiful result. It's absolutely remarkable. Okay. Another problem is feline currents. Again, I've kept throwing this around like in the past, the feline currents or the Birkeland currents. It's really not what we had in the ST5. We used the magnetic field perturbations and assumed it was currents. You can't do that. Maxwell tells us this is what you do. Now, if you have a single satellite, this is what we normally do. We just simplify this entire thing. We throw away a lot of terms. We assume it's infinite current sheet. We assume it's static, as we just spoke about. And if you have, on the other hand, you have more than three or more satellites, you can do the kilometer. You can basically do an integration. And what you gain is important because you don't have to assume it's static anymore. Because instantaneous, it's right here, right now. Okay, what you have to assume is the current within that triangle or that configuration is constant or quasi-constant. So you gain something. If you look below here, let's say 3 satellite passes, and you see this north-south structure that is supposed to be of fundamental importance for the Magnetosphere-Ionosphere system. It's certainly not static, right? Are you telling me it's infinite current sheets? I don't think so. So it's not static, it's not infinite current sheet. That means that any single satellite measurement ever made of this, you can throw out the feline currents because they're not right. Okay, we got to go a different route. Okay, so Shinotana did a beautiful study with Mutoba, where he took a swarm of satellites. It's 3 satellites, but 2 of them are close together. We can forget the third. They're close together, about 50 kilometers apart. And here's the all-sky camera as you see them whiffing across this fairly stable arc. And we looked at what are the currents looking like. Let's see them coming here. Whoop, here we go, whoosh. Okay. So if we apply that to this particular problem, and we do this kilometer technique, effectively what we do is we take one point of the A, the other one of A, a little bit later, and then C, and then we get a square. That's what is done with Swarm. So they get that square, that gives you ability to do the calculation, and we're good to go in principle. Here's the calculation of the result. This is the arc crossing. The kilometer technique is that, and the single satellite, the classical single satellite. And even in this case, which is very stable, and you're really passing through, it's all over the place. They do not disagree at all, these currents. So, what we learned from Swarm, and I think Swarm really only gives us a glimpse of the complexity here, is that even for the best case scenario, these stable or quasi-stable arcs, the currents are not static, they're not infinite current sheet, and they're not uniform over 50 kilometers. And that means that both these calculations break down. Darn it. Okay, let me just throw in a commercial here. There's a 40-year anniversary for the Ejima Pro Chamber picture, and they're going to have a special session at AGU, and I highly recommend you submit a paper to that. Shinotani is here, and I don't know if any of the other organizers are here. Okay, so let's move on. Processes, phenomena. What can you actually capture with this? Well, here's an example of these north-south structures. This is from Polar Earth camera, which is heavily used in the literature because it has some advantages. If you look at it, this is during a substorm. Do you see this very impressive? It's striking, this feature, right? No, it's not. It's a fuzzy mess. So we can zoom in, that's that fuzzy mess. But we firmly believe, and there are many papers that say this fuzzy mess is a fundamental feature of the Magnetosphere-Ionosphere system. But if you get this kind of imaging, you are challenged. And here's what it looks like in the low-res camera. So there's lots of structure. Okay, we're going to have to understand this feature. If we are to understand this feature, we need to take measurements and relate them to the emissions. And if you have that fuzzy mess, it's very difficult. With a 5-minute resolution, so it changes rapidly. Let's take Supermag here. There's Supermag. And this really is the best case scenario. I didn't pick that out. This is best case scenario. So this is taken straight from Supermag. You see the same feature here. And those are the vectors. But how on earth are we going to know anything about the gradients, what's going on in this feature? Not to mention that we are making interpretation of the ground perturbations in terms of the currents associated with this feature. That interpretation is not straightforward. So even the best case scenario, we have a challenge on our hand. This fundamental feature, we can't even address it because we don't have the observation. It's really, really a challenging task. Here's the other beautiful paper from Cousins and Shepard. So here are instantaneous solutions to the Superdome patterns. And here are the statistical patterns associated with that. And if you see, they disagree quite significantly in key regions. Certainly, these type of features are not repeated. And you see them over here too. They miss in amplitude as well as direction of flows. So there are limits to this, which brings us to a very fundamental question. Just because things are average and pretty doesn't mean it's right. Okay? Okay, if you have a double hump distribution and you take the average, you get something that never occurs. You have to be really, really careful. And I usually make a very simplistic argument. If I look at a traffic at a core intersection, traffic is going up and down at 50 miles an hour, it turns red. A little bit later, they go east and west at 50 miles an hour. If I take the average, it's 25 miles an hour bumping into each other. Luckily, that never happens. It's trivial, but this is what you effectively are doing in this. You're ignoring any kind of modes or system states here. You're just putting everything in, and you're hoping for the best. And that goes for all these models, not to beat up Superdome by any means. Okay, in fact, I beat up Supermag right away. So we use the state descriptors, and this is from our paper, where we looked into how is the average deviation or error in our solutions. We looked at the entire thing for 1 year. And what you see is that there's a distinct feature here. It's a cusp. Why is it there in the error? because we have no parameter in our multilinear regression that tells you about the cusp currents. So it's not parameterized, it's not going to show up. So there are limitations. It doesn't matter which model you do use. Let me put in another commercial. At AGU, we have another special session that I'm convening where we look into these features that are of fundamental importance, like north-south structures and so on. So basically relating the emissions to observations. If we wish to understand these features, we need not only emissions, but we need the observations. And here's the beautiful beading. And I just spoke to Tony, and you all need to read Tony's GRL paper that was just accepted, because apparently this problem is solved now. It's at least interesting, so please read it. And this beading develops into a substorm, and we can do that with this movie from Supermag. It's very fast because it's only 19 minutes. But you see it, and look at the position. A couple of features here. Off to the side that is really not, it still sees the substorm. That means the electric jet just to the east still sees the substorm, even though in the emission it's not clear. It picks up at the same time. The other one is, of course, at the head here, the vector becomes very big, and it's very erratic because the substorm is evolving. But it shows you a third thing, right? Darn it. Look at the red vectors. There are not many of them, right? It's over Russia, and this is what we do. So there are limitations to that too. Anyway, please submit a paper to that session. It'll be a great session. Okay, so let's go to conclusions. The derived quantities for measurements is based on assumptions that often are violated. So this is even going from the measurement to the parameters that we used for the modeling. We got to be careful about that. So the spatial temporal resolution limit the process and phenomena that can be addressed. Users should keep these assumptions in mind. Okay, providers should be open about the complexities and provide quality flags. We have very little quality flags in our field, and I really think we should be more generous with them. And relationship between large-scale and mesoscale processes should be emphasized. So you saw that vector off to the side, basically seeing the substorm, right? So you see the emission, but the system as such, there's a large-scale feature here that we need to address, and I think combining very local detailed measurements with the larger scale is a key issue here. Okay, so let's go to the last one. The holy grail of our field, in my mind, complete, continuous models of the electrodynamics. So let's start with one incident here. This is where Cameron, the undergrad, comes in. He superposed Supermag onto Ampere to see how do the ground perturbations and the feline currents, how do they relate? And if you look carefully, you'll see that not only the magnitude, but also the temporal behavior agrees tremendously. So this is a classical substorm, and I can let it run for a couple of times. And I think you can even see it at low latitudes, mid latitudes, how the feeding starts. There you go. So you start feeding the system. Okay, we can do a storm, which of course is a big mess, but we need to look at it anyway. It's going to blow up pretty soon. And as you see the feline currents go equatorwards, so does the ground perturbations. They always also move equatorward. And in fact, look how beautiful it is. If you look at this, you're going to see vectors, they're pointing that way, and as the system moves equatorward, whoop, they flip 180 degrees because these sheets are moving, okay? So it's not a temporal behavior, it's a spatial behavior to a large extent. But I thought it was very, very beautiful how they agreed, these two data sets. Okay, so combining them, we have an EarthCube proposal that it was really, I was thrilled to win it. Of course, then I got scared beyond, because we got to pull it off now, right? And then you start lining all the concerns and all the complexities that I've sort of outlined here today. And oh my God, this is not simple, right? So feel free to yell at me if we do not pull it off. But there's a third, if you see these paths over here, those are the SUSI, and the reason why they're included is that that's for the validation. SUSI, we can get conductances out. Lots of assumption going into calculating conductance from emissions, but at least it's something. And when you combine these data sets, you really have two equations with two unknowns, and the two unknowns are Hall conductance and Peterson conductance, so you get that out. People say it's a first principle solution. I say it's fudge factors. Effectively, you're fitting the conductances Colin Waters has tried it. If you combine this lot, you may come up with negative conductances. And the reason being the limitations in combining different things. So we need to be very, very careful when we do this. Okay. So here's how we do it. The measurements here is from the Earth cube here. We have the measurements. We got to derive some kind of parameters in here. And this is not trivial, as I said. Then we have to go do the uniform gridding. I discussed all that. When we have those distributions, we combine them in a first principle solution. But I think it's important that if you do this, you need to propagate the error bars through this system. Okay, and that's what has not been done in the past. You just assume the data is actually correct, and you should not do that. Okay, I recommended this a couple of times, that the users should have the ability to flexibly change things, and that's to see the limitations of the models and not just take them for granted. And this is ground truth. This is how it works. No, play around with it and see how it works. Okay, and of course, visualization and download, and this is where Robin Barnes is fantastic. He has this rule of thumb. It's a 3-click rule. You should never be more than 3 clicks away from the final product, and it should be publication quality. And I love that rule. Okay. Again, I have recommendations, but basically saying you have to be careful about combining this. But comprehensive objective validation of the solution, NSF, you gotta fund us to do this. It's needed. I really mean it. We get jumping to conclusions about physical processes that really should not have been made because the validation is not there. Okay. Okay. So, in principle, we are done. But of course, I can't help it, so I got a bonus slide. Okay. So, I've been beating up global solutions. Let me turn it all the way upside down. How about the local solutions? Okay, well, I went to Seville last year, and I went to the cathedral. They have the world's biggest gothic cathedral, and it's incredible. And everybody was taking pictures of the gold and the windows and everything. And I looked down at the floor, and I saw this, and I thought, that is a cool floor. Look at that star there. I like it. Okay? Of course, it's kind of a nerdy thing. But then I look up and look at the bigger floor. And I see, no, it's not stars. It's actually squares. It's a bunch of squares with some corners cut out. Okay? So what happened here is that I made a conclusion on local measurements about the global pattern. And here's where it is, if you can't find the star. It's almost difficult if you don't outline it, right? And what's the point here? The point I'm trying to make is, if you make conclusions about the global pattern from local measurements, it's very, very dangerous. Thanks a lot.